All right, so we're going to take this expression and put it here. And we want to come up with strings that match that regular expression. So who wants to try first? Come on, quickly. Just one string.
Okay. Just one string will do?
Yes, just one string.
Yeah, that's it.
Okay, good. Another one? Who else can give me another one? Okay, very good. Is there away?
Yes.
All right. And your friend? Okay. Okay. Another one? For the same regular expression? Yes. Yin Jen, right?
Yeah.
Okay, very good. Clear for everybody? Everybody's okay with that? Next one. So who wants to try this one? Yes. Okay, that's good. You are? Thank you. Another one? Arnold.
That's interesting.
Okay, good. And another one? Alright, if I try A-E-E or A-D-D-E. What's happening here? Hmm? What are you using? You're not using Rupala, right? Oh, really? Very strange. Does it have anything to do with the... No. Can you change the version? Uh-huh. That's interesting. I had no idea that the previous version of Ruby would would match. So there's a discrepancy between theory and practice. The string should be matched fully. A to the E should be matched fully. However, there's a particular kind of heuristic for matching called greedy matching that prevents the library that performs this matching to match the E. That's because between D and E, the library will find an infinite number of matchings for the empty string, right? So this question mark is either 1D or the empty string. That's what it means, right? So the D question mark, the empty string instance of the D is matched an infinite number of times, right? This means infinite number of times, right? And then sort of it's like it never gets to, the matcher never gets to see the E. So it doesn't match the E. All right, obviously if you delete this question mark here, this will solve the problem, right? The reason for this is that this heuristic avoids a potentially exponential blow up in an integral transformation. We're gonna talk about this in one of the, I think the second or the third problem question. We're gonna talk about this, right? So that's what it's trying to do. It's trying to be more efficient, but in that way it is more restrictive. The good news, on the other hand, is that you can always find an equivalent regular expression that doesn't have that problem, right? So it's up to you, to the programmer, to foresee that this greedy matching problem will occur and avoid it in practice. This is a peculiar problem of this implementation. Ruby relies on a regular expression library that is used in practice. There are many other implementations that do not suffer from this problem, right? So remember that in practice sometimes things are not implemented exactly as the theory requires. Is this clear? Yes. Then E will be matched. That's true, because so then you're going to have the question mark, and that will also match D, because now E will be tried first. Okay. So it's a matter of committing to whatever you can commit as early as possible. So E is noticed first and then matched. Yes. Again? To emphasize the fact that you have this problem. Okay? It's a legal regular expression. Okay? And if I would put it in Lex, or you notice, right? If I put it in a previous version of Ruby, there's no problem with it, right? Works fine. But it's just a matter of implementing greedily a certain matching pattern. Okay.
Is this only for Ruby or?
So grep will have the same problem. Anything that uses that particular library, it's the standard library in Unix for regular expressions, for regular expression matching, right? Which is typically linked into grep. That's what it was. That's what the library was produced for, to create the command grep, right? And then it was important, and it's available as a library. You can put it in any program, right? There are other implementations, but if you want to be theoretically complete, you have to perform a transformation. We're going to discuss it soon. You have to perform a certain transformation that is potentially exponential, right? That may take exponential time. I'm assuming, I'm not absolutely sure, but I'm assuming that this is the reason why they did not want to use the transformation in the implementation of the library. Okay. All the more that it's always possible to come up with a regular expression that doesn't suffer from this problem. Okay, let's do the last one. Okay, who wants to try? 3 more. Okay. So BCTE. Any BC could be replaced by an A. You're John, right? Not. It has to. The blue part has to cover completely, right? Cover the string completely. Okay. And it's a line? No. Liming. Okay. So you like repeating, right? You don't like to next one to write a different one. You could have written like ATTE, BCD, for instance, BCDD. But once you've found one pattern that works, you have to repeat that one. So, what's Rizal? Was that the? That's you. What's your name? Van Ben. Okay. Okay. So, questions about regular expressions? They're pretty easy. They're a very useful tool in general. They're a useful tool especially in creating, in writing compilers, in developing compilers, right? The compiler has several phases. The first one is syntactic analysis, where it is decided whether the program is syntactically correct. And you get these things called syntax errors. You've probably, you've surely seen them. And that is stratified in 2 layers, right? There's a layer which we call lexing or scanning, where the basic elements of the language are identified, like integer constants or identifiers or operators. And then the second phase is parsing, right? So this phase of scanning, lexing, is achieved via a regular expression matcher, right? All the all the basic language elements can be identified by regular expressions. We can have a regular expression for instance, floating point numbers, right? We've seen one in one of the lectures. We can have a regular expression for identifiers in C, right? What would be a regular expression for C identifiers? C variable names. What would we have? Small a to z, capital A to capital Z, and underscore, right, followed by small a to z, capital A to capital Z, underscore 0 to 9. Actually, I'm not sure I need this one, so close square bracket and star, right? So, and obviously everything that we've given here is a C identifier, but so is 1, 2, 3, for instance, right? So these would be C identifiers. Prolog identifiers, right, we would have to play with, they start with, if it's variables, they would start with capital letters or underscore, so this would be prolog identifiers, right? And A1 to 3 is no longer, oh, it is, right, but A1 to 3 is no longer a prolog variable. And so on, right? So there's this layer at the, which is precisely the first thing that a compiler does, converting or detecting basic language elements in your program, and that is done via a regular expression match. Let's move on to exercise 2, and we want for the second regular expression to define a DFA that accepts the language specified by it. So I'm going to do the following. I'm going to, this is the expression. I'm going to create a canvas out of my head. Alright, all I want is a canvas, so alright, so you have the regular expression here, and on the white area we want to draw the automata. Okay, who wants to try? Slide? Yes, can you try? use the pen. Use the pen. Press Ctrl 2. Ctrl 2 to get it to handwriting mode. Okay. No, that's not acceptable. That's not something you can write.
Clear it.
Control Z will undo.
Huh?
Control Z will undo. So it's a single symbol per arrow. One symbol per arrow. No, one symbol per arrow.
Okay, I get it.
Okay. Can it be made simpler? Can you reduce the number of stages?
Oh, yeah, can. Oops.
Might not be able to go that far.
This one should go back to the...
Yeah, so. Okay, good, better. Okay, thank you. So, this is the automaton. Normally we would denote the states by something like 0, 1, 2, especially because they don't have to be numbers, but in general, if we implement this, can we stop that? It's what? There's no paper here. No, but it's not. Oh, it's not a printer. It's me. Sorry. Too many things on the desk. So we will put, let's say, states. And then, if we really want to be faithful to the regular expression, right, the question mark on D should result in what? We should have a transition here denoted by epsilon, right? Once we do that, this is no longer a DFA, right? We call this DFA for deterministic finite automaton, right? Finite number of states. Deterministic, why do we call it deterministic? Because from every state, each symbol takes us to a different state, right? And also we don't have epsilon transitions. Once we add epsilon transitions, we progress into an NFA. Because if we have epsilon transitions, we don't know what's going to happen next. Should I perform the epsilon transition, or should I perform the transition on D? Right? It's not clear looking at my input what I should do. When we use the word deterministic, it means that I should always have one thing to do next. Okay? So we progress into an NFA. The NFA allows us to go from one state on the same symbol to multiple states, right? Also allows epsilon transitions. So NFA appears to be more general, right? And NFA in general will allow a more direct implementation of regular expressions, right? Because regular expressions have these question marks, and stars. So it looks like we always have the trouble of having to deal with the empty symbol. Okay, but it turns out in theory that this conversion is always possible. I can always take an NFA and change it into a DFA, convert it into a DFA. Always possible, right? So it's mathematically provable. However, if I have a number of states n here, it's likely that I'm going to have 2 to the power of n here. So the conversion itself may take exponential time, and it will result in a DFA with exponential number of states. So if we want to faithfully implement the DFA, right, we might have to deal with decreased efficiency. In practice, nobody does that. In practice, regular expression matching is done via the greedy, well, nobody. Some will do. But in practice, most often you'll see regular expression matching based on the greedy heuristic that we have experienced in Ruby. Okay? So this is exactly the reason. So it is always possible to get the correct automaton, right? The one that would accept ADDE. You see, ADDE is a correct string. I go to state 2, I take this transition twice, and then I take E, and I'm still in a final state. This is the final state, by the way. It should be double circled, right? And this is a correct string. However, what the regular expression matcher does is takes the transition on A, that takes the transition on D, that takes the transition on D again, right? It checks for the transition on epsilon before checking for the transition on E, right? And it sees that it can perform an infinite number of epsilons, and will detect that it's a potential infinite loop, so it will say, well, the string that I can match is this guy. I will never go and try the E. So that's what the regular expression matcher does, and it is, in fact, wrong. Is this clear? Okay, so this is the DFA, and later we're going to try to implement it. Exercises 4 and 5. But before we go there, we would like to write a regular grammar. So I'm going to leave the expression in the same format. I'm going to leave the expression, and the regular expression that you see highlighted in blue, and then somebody should come and write the regular grammar. Okay, who wants to help me? So tut03 was just now, right?
Yes.
Answer just now. Unbin? That's right. Well, you'll learn in the process. Come. All right, so can you draw again the automaton that we have just had on the whiteboard? Was that? Yes, use that. You can write. So first of all, draw the automaton that we have. Sit down.
How to erase.
Ctrl-Z. Look at your computer screen, you don't. All right. So now, what does a grammar do?
Formally define.
Define what?
Define the expression.
A language, right? So how do we do that? We do that by starting from a start terminal and producing production rules, right? So here, it's very simple. We attach a non-terminal to every state. So now, since we haven't named the states yet, let's name them with capital letters. So A, B, C. Use A, B, C for the state names. All right. So then, watch with the computer screen. Why are you looking on the? It's easier to look at the computer screen. So then, let's say that A is the start terminal because it's also the start state of the automaton. And we can say from A, we have an arrow, right? It's a production rule. And we have small a and C. Small a and capital C. Small a and capital C, right? So A, capital C. Okay, so that's one rule, right? Can you write the rest of the rules? Okay. So it becomes very simple. All right. And what else needs to be there? Since C is a final state.
how to
Epsilon. Yes, very good.
huh?
That's beta. It's like a 3, but on the reverse.
Ah.
Ah. All right. That's. All right. So these are the rules. Okay. Thanks. All right. What does a grammar do? Well, starting from the start terminal, we perform derivations, right? And we do that by building a parse tree. So we start from the start symbol. So let's say that this is the start state. A is the start symbol. And we can pick any of the rules and perform a derivation. A, C, for instance. So now we look at the frontier of the tree, current frontier of the tree, and we notice there's a non-terminal there, and we can expand this further. We pick a rule for C, any rule we want, right? And we perform further, sorry, A, E, and C, yes. And then we can do C, D, and another C, and then maybe we do epsilon. And we keep doing that till at some point we're going to reach, we're going to get a tree that has a frontier that has no non-terminals, and at that point we have generated a string of the language, right? So this is the frontier, and you can read it like sort of from left to right as much as possible. I know that, you know, my drawing skills are not that great, but it's A, C, D, E, A, C, D, epsilon. Epsilon doesn't count, so A, C, D, not A, C, D, A, E, D, right, is a string of the language. So now you can easily see the correspondence. If you look at these rules, right, every time you perform an expansion, you're essentially traversing one arrow in the automaton. So in the end, all the expansions will only lead you to, you can only get an expansion that doesn't have non-terminals only when you would follow arrows in the automaton and get to the final state. And at that point, what you have on a frontier is a string that you would see on all the arrows that you have traversed in order to reach there. Right, so there's an immediate correspondence between the automaton and the grammar. So this would be the regular grammar that generates the same language as the automaton accepts. Notice the difference. The grammar is a generative mechanism, so I can randomly generate strings from the language. If you tell me, give me a string of this language, I can immediately cook up one, right? I can do some derivation until I get no more non-terminals on the frontier, and I say this is one string. Whereas the automaton is an accepting mechanism, right? You give me the string and I tell you whether it's in the grammar or not. So both of them are important. The automaton is important because you want to perform syntactic analysis, for example, but the grammar is important because it tells you sort of what is the structure of the language and what kind of expressions can you write in that language. So often in programming languages books, especially in older ones, it's in more recent times programmers are not so theoretically inclined. So showing a programmer a grammar of the language that he's supposed to use now scares people off. But if you look at older C books, for instance, at the end of the book you would have the grammar of the language. C books, Pascal books, they used to come with that, and that was supposed to be something a programmer was expected to understand and use in writing correct C or Pascal programs. Is this clear? Okay, let's move on and try to write some code. So the next two questions ask for implementations of DFAs. So we're going to have two implementations. The first one will ask for a C procedure that implements the automaton equivalent to the second regular expression of exercise 1. So let's go to code blocks. I'm going to close this project, and you're going to start the project for me to implement a DFA. Who wants to try? Kalam? One Kalam? Okay. What are we going to do? No, close that project.
Oh.
So file, close project. Close project. Close project. Alright, so create empty project. And we call it tut03. Exercise 4, E4, group 3, right? G3. Okay. Now we create a new file. Empty file. So yes. So yeah, pick the name of this project, and delete the last two characters, and get the name of the file. Okay, good. So we're going to write a function called accept that takes in a string and returns 0 or 1 depending on whether the string is accepted or not. And the implementation, this implementation, we want to make it in the form of a switch on the state, and inside every case, we want a switch on every character. Now, having the switch is not enough. We have to loop through the elements of the string. Very good. So, while s, okay, s, is that I? S, I, right? Not equal character of x is 0. Alright. So now we switch on the state. We're going to consider that the error state is -1. Right, that's what we're going to use. And now for every state, So we're going to have three states, case 0, 1, and 2. Start from state 0. So for each case, we have another switch on the current character. And every time we say which is the next state.
How can I format the?
Again,
How can I format the code?
format.
Yeah.
You select everything and right click, and there's a format file. So after switch SI, you should have a brace, right? An open brace. And after switch state, you should also have an open brace.
Oh, yeah.
So switch followed by an open brace. Alright. So put all the brakes everywhere, don't leave anyone out. Don't leave any of them out.
The state of A should be, should be 2.
A should be 2, B should be 1. Okay, brake, go to case 1. And have a switch inside there as well.
how should we deal with the empty string?
Or should you what?
Deal with the empty string in this state.
You don't put it there. Otherwise, you don't. Otherwise, you don't have a DFA. We just discussed that it's some sort of optional, right? You don't put it. Make sure you put all the defaults, and whenever it's necessary, you make the next state to be the error state. -1. Make it -1. Okay. All right. So let's write a main to test that the program works.
Sorry?
Let's write a main program.
Yeah.
A main function. Test that the program works. Yeah, put a string. A, B, A, B, D, E, D, E, D. Okay. was not accepted? Let me check what's happening.
Oh, yeah.
So what's the, yeah, I++ is important. What's happening, what's the loop condition? The loop condition is s not equal, si not equal to 0, and state is not -1, right? What? Didn't manage to work? Control shift escape. And no processes, please. CB console runner, the C1, okay, that one. Okay, close that window. And let's try to rebuild. There's an error. Where is it? Oh, try again. Try to build again. Again, Control Shift Escape, and look for that file. Go down to T. File starting with T. Okay. There's another one. Don't go. Just above. Yeah. Not TP. Not TP. There's a T something. Do I see? No, I didn't see. Okay, good. So leave it the way it is. So close that window and try to build again. All right, run.
Oh.
Accept this one. Okay. Good enough. Thank you. So your column, right? All right, last one. Last exercise. Okay, so I want to make some changes to make it more manageable. So we want to take this piece of code. We're going to have another implementation of a DFA, right? The deterministic finite automaton. Okay. And, well, to make it more manageable, I'm going to say here s minus character A. and then we're going to deal with only characters between A and E, sorry. So star S greater equal A and S less equals E. Then we're going to do this. Otherwise, we're going to go to the error state. Alright, so you see we have a program template, and all we are allowed to do is to make changes in these places that are left unfilled. Right, so I'm going to delete this entire thing. Right? So what should I put here? What's the value of n? Three. Very good. 3 states, right? What's the value of m? 5. 5 symbols. Final state. Well, we can decide later what it should be. So 3 rows in the array, right? First row are transitions from state 0. On symbol A, we go to state 2. On symbol B, we go to 1. On C, -1, -1, -1, right? Error state. On from state 1, on symbol A, we go to -1. On symbol B, we go to -1. On symbol C, we go to 2. And then -1, -1. From state 2, on symbol A, we go to -1, error, right? On B, -1. On C, -1. On D, 2. 2 as well, right? Final state, okay, and this is it. I'm going to go and steal a main from a previous project. So I'm going to steal the main from here. No. Alright, so when we copy from Acrobat Reader, some of the characters do not have the correct ASCII codes, and we get output. Okay, so this is a alternative implementation for DFX. Both kinds of implementations can be generated automatically from regular expressions. And for instance, a program called Lex, or the more recent version of that program, which is called Flex, is capable of doing that. Right, it's a tool for generating lexical analyzers for compilers. And we have a specification of basic elements of the programming language, and it will generate a C program that accepts them. Okay. Okay. Questions? All clear? All right. You're free to go then. See you next time. If you want to stick around and chat, if you have more questions.